The story of the Cathedral of the Infinite Arch is not a tale of kings or battles. It is a story told in stone. A meticulous, century-spanning epic of logistics and unyielding human effort. It is the history of men who devoted their lives to a project they knew they would never see finished. We journey now to the 13th century, to the heart of France, where faith met physics and the master masons began their impossible climb. The building of this great church required immense funding and a sophisticated supply chain that stretched across the medieval landscape. Chapter 4: The March of Stone and the Mule Train Economy. The weight of the project was literal. Thousands upon thousands of tons of stone were required to raise the walls and vaults. The primary material was limestone, quarried from deep pits, sometimes many leagues away. Transporting stone over any significant distance was tremendously expensive. It was, in fact, often considered uneconomical. This heavy burden meant that whenever possible, builders used stone quarried locally. But for the specialized structural elements, the precise blocks of free stone, long-distance transport was necessary. This logistical nightmare dictated the entire workflow. The quarry, site of prefabrication. To minimize the crippling costs of hauling raw bulk, a pivotal decision was made at the quarry itself. The raw blocks were often too unwieldy and too heavy to move efficiently. Therefore, much of the stone was prepared and shaped, a process called dressing. This happened right there, at the quarry face. The skilled stonecutters plied their mallets and chisels, transforming rough limestone blocks into precise, squared ashlar blocks. Templates, created by the master mason back at the cathedral site, were brought out to ensure perfection. This allowed for a degree of standardization, a medieval form of assembly line production. The logistical difficulty of transporting rough blocks meant that the master mason's geometric instructions had to be transferred to these distant quarry workshops perfectly. This organizational necessity forced an early, high degree of standardization into the construction process. Once cut, they were loaded onto the transport network, financing the Hall of Giants. The true cost of this monument was the skilled labor. But the funds to pay this labor and to move the material had to be meticulously gathered. Financing came from the vast wealth generated by the redistribution of agricultural surpluses across the church's lands. But the cathedral chapter, the senior clergy overseeing the build, were resourceful managers. They created ingenious local fundraising systems. Clerics who were tardy or committed minor transgressions might be fined, and those funds diverted directly to the building costs. Most lucrative of all was the religious spectacle. Holy relics, revered artifacts believed to possess spiritual power, were sent on grand tour. Pious pilgrims would flock to see them, offering donations that filled the coffers. Cash that was immediately fed back into purchasing timber or paying for transport. The church also employed a unique form of spiritual barter. Since the skilled laborers demanded high wages, the church often found its cash funds constrained. They needed common, unskilled labor for the most arduous tasks, like dragging the cut stone blocks. They offered indulgences, forgiveness of sins, to ordinary citizens who participated willingly in the physical work of the Lord. This cheapened the actual financial outlay, but bound the cathedral project deeply into the moral and spiritual economy of the era. It was an ingenious system, exchanging eternal salvation for backbreaking physical effort, ensuring that the heaviest blocks still reached the site. The stones were hauled by ox or horse-drawn carts and wagons, a relentless, slow procession along medieval roads. Consider the economy of construction. It relied on three pillars. First, the agricultural surplus, providing the capital. Second, the relictor, creating immediate cash flow from pilgrims. And third, the indulgences, spiritual forgiveness, traded for the sweat of the heavy transport. Chapter 5. The Symphony of the Hammer, Life in the Lodge. The cathedrals were not built by fixed city populations, but by a transient, highly specialized workforce. The stone cutters and masons were nomadic professionals. They moved freely across Europe, following the great construction sites, where their specific skills were in high demand. The ecosystem of labor. At the construction site itself, the workforce was stratified. At the bottom were the rough laborers, responsible for digging the foundations, transporting materials within the site, and removing earth. These men were paid. Records exist confirming wages were standard for this work, countering the myth of purely voluntary labor. Above them were the skilled tradesmen. The rough masons worked on the basic wall fabric, laying irregular rubble stone. But the elite were the Freemasons. These were the skilled tradesmen who could fabricate the precise elements. The corbels, the window tracery, and the precisely fitted ashlar blocks. These specialized workers lived together in a complex, temporary structure on site, known as the lodge. This lodge was more than a dormitory. It was a professional hub, where skills were passed down, and where the necessity of supporting mobile, highly skilled tradesmen directly led to the establishment of formalized guilds. This environment served as the cradle for the later, honorary institution of Freemasonry. Payment by the piece, the banker mark. The relationship between the master mason and the workforce was fundamentally economic. Masons were typically compensated through a piecework system. They were paid for each individual stone they cut, shaped, and prepared for placement. To track this pay, and to ensure a transparent accounting system, each finished block was inscribed with a unique symbol. This was the banker mark. The banker mark was a small, personal geometric symbol, identifying the specific mason responsible for the final dressing of that stone. This mark was used to calculate their wages. But this system had a powerful secondary function: quality control. If a structural weakness or fault developed years later, the mark could theoretically be used to trace the stone and the subsequent liability back to the original craftsman. The banker mark was more than a payroll tag. It was the medieval equivalent of a permanent contractor's liability signature, guaranteeing standards for a structure meant to last centuries. The master's compensation. At the apex of this complex organization was the master mason, the supervisor and architect. He was highly compensated. Records show that a master mason could earn a substantial annual salary, sometimes exceeding £50 a year. His contract often required his continuous presence on the construction site, with strict limits on how long he could be absent. The project demanded his constant oversight. Tools of transformation. The masons used a specific array of tools, each designed for a different stage of stone dressing. The tools themselves tell the story of the block's journey from rough rock to finished architectural element. Let us visualize the tools. First, the point chisel, used for initial shaping, leaving deep, rough indentations. Second, the claw chisel, used for intermediate refinement, leaving parallel grooves and texture. Third, the flat chisel, or axe, used for fine dressing, creating a smooth, finished surface. And finally, the set square, to ensure geometric accuracy. The constant movement of skilled masons, the financial complexity of piecework, and the long-term liability inherent in the banker mark system all underscore one truth. The medieval cathedral was not merely a spiritual endeavor, but an advanced and relentlessly efficient industrial operation. This logistical complexity laid the groundwork for the structural miracles that were about to be lifted hundreds of feet into the sky. Chapter 6: Rising Walls and the Treadwheel Engine. The most demanding challenge of the construction phase was the vertical ascent. Lifting massive blocks of cut stone, sometimes weighing over a ton, dozens of meters into the air. This required exceptional engineering for the time. The foundational lifting mechanism was the treadwheel crane, known in Latin as the Magna Rota. This was not a machine powered by animals or by water, but by men. It was constructed primarily of durable hardwood, such as oak, and featured a massive hollow wooden wheel. This wheel was formidable in size, typically ranging from 4 to 6.5 meters in diameter. 2 to 4 workers would climb inside this large wheel, walking continuously, to generate the necessary torque. This human-powered engine was remarkably effective for its era. It provided reliable, precise control for vertical lifts. Through a system of pulleys, often configured as a pentaspasto setup, the treadwheel crane could hoist significant loads, typically ranging from 1 to 3.5 tons. However, the technology faced intrinsic limitations. The practical vertical lifting height was restricted, usually to about 15 to 18 meters. Since the main nave vaults of major cathedrals often rose much higher than this restriction, the higher portions of the structure required a complex, multi-stage lifting operation. Stone blocks had to be lifted, transferred to an upper platform, and then lifted again by a second, higher treadwheel. This multiplication of effort exponentially increased both the time required and the inherent risk of accidents. Scaffolding and the architecture of access. As the stone walls rose, a parallel structure of immense wooden scaffolding was built around them. This was the temporary infrastructure necessary to support the workers and to serve as the base for the upper lifting stages. This scaffolding was anchored directly into the permanent stone fabric of the cathedral. Long wooden beams, known as putlogs, were inserted into purpose-built apertures in the wall called putlog holes. These holes can still be seen today on many medieval structures, indicating the horizontal axes along which the scaffolding rested. The architecture itself was designed not only for ultimate permanence, but also to facilitate its own construction. The placement of these strategic anchor points was part of the master mason's geometric plan, turning the rising stone structure into a temporary machine for positioning materials and men. After the section of the wall was completed, the putlogs would be removed, and the holes either filled in or occasionally left open. Construction was a constant, repetitive cycle, dependent on the rhythms of nature. Masons could not lay stone in freezing weather, as mortar required stable temperatures to set properly. This seasonality forced lengthy winter delays, a natural constraint that contributed significantly to the century-long construction timelines. Chapter 7: The Sky-High Solution, Designing the Flying Buttress. The ambition of the Gothic age was to reach impossible heights and to flood the interior with divine light. This aspiration created a profound architectural dilemma. Earlier Romanesque structures relied on massive, thick walls, pierced only by small windows, to bear the weight and resist the immense outward push, known as lateral thrust. The Gothic desire for soaring height and vast expanses of glass demanded thinner walls. These slimmer walls, however, could not withstand the crushing horizontal forces of the stone vaults above. The revolutionary answer emerged in 12th century France. It was the flying buttress. The flying buttress is an external support system, instantly recognizable as the signature of Gothic architecture. It consists of a sturdy outer pier, or column, placed away from the main wall. From this pier, an arched stone bridge, called the flyer, springs across to connect with the upper section of the fragile wall. The genius of this design is its efficiency. It precisely captures the concentrated lateral force exerted by the heavy stone roof structure, and transfers that destructive outward thrust safely down, through the angled flyer, to the massive external pier, and ultimately into the ground. By diverting this force externally, the inner wall was liberated. It was no longer required to be an oppressive structural mass, but could be transformed into a delicate, soaring cage of glass. Engineering as a hypothesis. The development of this structural device was a high-stakes gamble. Medieval builders did not possess modern mathematical analysis tools. They relied on geometric principles, empirical knowledge, and a process of intense architectural experimentation. Every great Gothic cathedral was a structural hypothesis, made visible. The master masons were continually pushing the boundaries of physics. Often, the need for the buttresses only became horrifyingly clear after the walls were partially erected, or when the structure began to visibly deflect or even fail under the weight of the vaults. The flying buttresses at the Cathedral of the Infinite Arch and many contemporaries were not always part of the original blueprint. They were often structural improvisations, rapid external reinforcements, added when the master mason realized the initial design could not sustain the vertical ambition. The structure's permanence depended on learning from these partial failures and adding the buttress as a necessary reinforcement. Chapter 8: The Great Vaulting Crisis. The highest point of danger, and the pinnacle of the master mason's geometry, was the construction of the stone ceiling, the vault, high above the central nave. The vaults served a dual purpose. They provided critical structural stability to the entire building, reinforcing the walls against lateral loads. Crucially, they also provided fire protection. The massive timber roof installed high above the stone vault was a constant fire hazard. A stone ceiling created a barrier against total destruction. The geometry of compression. Stone vaults cannot be built freehand in the air. The construction required the placement of immense temporary wooden frameworks known as centering. This massive scaffolding supported every stone of the arch, holding it in perfect position until the final locking element was secured. The entire geometric plan for these complex curves, the diagonal ribs and the connecting web stones, was first calculated and drawn in full scale on a plaster floor set aside for this purpose. The tracing floor. The structure remained unstable, supported only by the creaking wooden centering, until the definitive moment. This moment arrived with the insertion of the keystone. The keystone is the central, wedge-shaped stone placed at the highest point of the arch. Once this final stone was tapped into place, the structure instantly changed. The entire arch transitioned from a passive, supported framework to an active, self-supporting structure. The compression forces locked the stones together, making the wood centering immediately obsolete. The removal of the centering was the ultimate stress test. The moment the temporary wooden support was taken away, the structure underwent its ultimate trial. If the buttresses were incorrectly placed, or the stone geometry was flawed, the entire roof could collapse, wiping out decades of labor. The silence that followed the removal of the centering, confirming the arch was locked in perfect, eternal compression, was the master mason's greatest triumph. Chapter 9: The Roof of Giants, Timber and Lead. Above the stone vaults lay the final structural layer, the roof. This layer was entirely made of timber, and required the consumption of a staggering volume of wood. The construction of the immense timber frame required large, straight beams. To obtain the huge tie beams necessary to span the wide nave and choir, and to handle the high pitch of the roof, massive, ancient trees had to be sourced. The timber frame served a crucial structural role. It was detailed to act as a rigid structural cage, distributing the significant forces generated by high winds down to the stone buttresses below. The requirement for these specialized structural timbers meant that the construction project had a massive, often distant environmental impact. The cathedral's material existence necessitated the felling of entire, primeval forests, linking the urban religious project to the distant medieval wilderness. Once the timber truss was completed, it was covered with metal sheeting. This was typically a thick layer of lead. The lead provided essential waterproofing, protecting the expensive timber and stone structure from the elements. However, the lead itself added immense, unrelenting weight to the structure. It was this heavy load of timber and lead, resting upon the stone vault, that absolutely necessitated the entire, complex system of external supports, making the flying buttress not a decoration, but a mandatory engineering requirement. Chapter 10: The Quiet Legacy. The Cathedral of the Infinite Arch was a monumental act of faith, but also an exercise in profound patience. The time required for completion was not measured in years, but in generations. Even the relatively fast construction of Notre Dame in Paris took 182 years to be considered largely finished. Because the construction span was so vast, often multiple styles of Gothic architecture appeared within a single structure, reflecting the different tastes and structural knowledge of successive master masons. No single master mason, or chapter member, or even ordinary parishioner, could realistically expect to see the finished work. This reality demanded an almost unimaginable level of long-term commitment. The people involved, the skilled mobile masons, the laborers paid in kind, the donors who contributed their annual surplus, were committing their lives and wealth to an outcome that lay hundreds of years in the future. The cathedral stands as the ultimate testament to anonymity and deferred gratification. The building was never a project pursued for immediate financial profit. It was a monument to the community, a symbol of civic pride, and a house dedicated to the divine. The thousands of anonymous hands, the quarrymen, the carpenters, the masons whose signature banker marks are hidden in the unseen joints of the stone, labored diligently toward a fulfillment they would never witness. The finished cathedral, towering over the city, stands today as the ultimate testament to anonymity, to shared sacrifice, and to the architectural humility of those who build not for themselves, but for the infinite clock of history. The work continues, slow and rhythmic. In the darkness, Chapter 15, the language of the tool marks. Every stone used in the Cathedral of the Infinite Arch bears a subtle, indelible story. It is the story told by the marks left by the mason's tools, a language that speaks of speed, skill, and the pressures of piecework labor. The final surface texture of the stone was not random. It was the result of a deliberate, step-by-step process, mandated by the master mason for specific aesthetic and functional reasons. The point, the claw, and the axe. The journey of the rough block began with the point chisel, a heavy tool used for aggressive, rapid material removal. This left deep, chaotic indentations that had to be eliminated for structural integrity. Next came the claw chisel. Its serrated edge systematically erased the deepest marks. leaving behind distinctive, parallel grooves, a mark of intermediate refinement. Finally, the flat chisel or the axe was used for the delicate, final dressing. This smoothed the surface, achieving the flawless finish required for the highly visible elements, such as the column shafts or the precise edges of the ashlar blocks. The finish of the stone was a signature. A coarsely dressed stone might indicate a block intended for the unseen core of the wall, where rapid work was acceptable. A finely dressed stone indicated a crucial structural or visible element, justifying the higher wage paid to the artisan who took the time for perfection. These minute tool marks are still visible today, a quiet, permanent record of medieval labor efficiency. Written into the rock itself. Chapter 16. Iron, the Invisible Structural Secret. Although the Gothic Cathedral appears to be a structure built solely of stone and light, its stability relied on a crucial, often invisible element: iron. Medieval builders understood that stone is superb under compression, but fatally weak when subjected to tension or stretching forces. To overcome this inherent weakness, especially in critical areas like the upper walls and the thin window tracery, iron was employed as a hidden reinforcement. The clamps and the chains. Iron clamps and tie rods were frequently inserted into the masonry joints across areas of high tension. These iron elements acted like internal chains, binding the stone structure together, particularly in the upper stories or around the massive stained glass windows. They provided the necessary tensile strength, keeping the stone joints tightly closed and preventing the delicate structure from spreading or cracking under pressure. This iron was costly, and its use required specialized smiths and immense effort to position precisely within the rising stone walls. The master mason had to integrate the craft of the blacksmith with the art of the stonemason, creating a hybrid structure of stone, mortar, and hidden metal sinew. The true strength of the towering stone wall was often the invisible, unyielding grip of the iron embedded deep inside. Chapter 17. The Secret Society of the Traveling Master. The Master Masons and the elite Freemasons were professionals defined by their mobility. They were not tied to one city or manor, but traveled freely across Europe, following the largest projects where their specialized skills were in highest demand. This itinerant life, combined with the necessity of protecting their complex geometric knowledge, led directly to the formation of the Masons' Lodge. The Lodge and the Guild. The Lodge was a large, temporary structure erected adjacent to the construction site. It served as a workshop, a dormitory, and a vital community center for the transient workers. Within the lodge, the master mason maintained the tracing floor, where the sacred geometry of the cathedral was laid out in full scale. This knowledge, the practical ability to transform simple geometric ratios into massive, stable structures, was the mason's most protected secret. To regulate quality, wages, and the transmission of this protected knowledge, masons formed the most influential and secretive of the medieval guilds. This formalized system of professional secrecy, the rituals of recognition needed by traveling masons, and the strict control over skill and entry, laid the foundation for the later, more symbolic institution of Freemasonry. The cathedral was not just built by stones, but by an organized, highly professionalized workforce, bound together by common skill, high wages, and a shared commitment to a secretive, divine geometry. Chapter 18. The Infinite Line of the Builder. The construction of the Cathedral of the Infinite Arch was the ultimate exercise in architectural humility. No single generation saw its beginning, its middle, or its end. The master mason worked with the certainty that his design would be finished, modified, or potentially corrected by successors he would never meet. The building process became an act of anonymous contribution, a slow, rhythmic commitment to a future that exceeded the human lifespan. The masons who cut the quarry stones, who operated the treadwheel crane, and who inserted the final keystone are largely forgotten, yet their geometric principles survive. Their banker marks are hidden in the unseen joints. The sheer weight of their collective effort, their patience, and their precision engineering still presses against the earth. The master mason's true legacy was not the specific stones he laid, but the unbreakable, geometrical instruction set, the design system that allowed a project of impossible scale to survive the passage of centuries and the failings of successive human hands. The sound of the chisel has faded, but the silence is filled with the weight of the structure, eternally locked, eternally pressing into the ground. The work continues, slow and rhythmic. In the darkness, Chapter 19, the whisper of the gargoyles function over fear. High above the massive, curving stone of the flying buttresses stand the cathedral's watchful protectors, the gargoyles and the grotesques. These figures, often monstrous and exaggerated, seem designed to ward off evil spirits, or perhaps to reflect the imperfect, terrifying world outside the sanctuary's walls. But their purpose was profoundly practical and deeply hydrological. The term gargoyle derives from the Old French word gargouille, meaning throat or gullet. The carved figure was not mere decoration. It was an essential component of the cathedral's drainage system. Rainwater running off the vast, lead-covered roof had to be diverted. If allowed to stream down the delicate stone surfaces of the buttresses and walls, it would erode the mortar joints and eventually compromise the structural integrity. The gargoyle served as the terminal point of an internal roof gutter, projecting the collected water far out and away from the priceless stone fabric below. The stone sculptor, the artisan who brought these monsters to life, was therefore an engineer of fluid dynamics, tasked with ensuring the structure's long-term survival through practical plumbing. Conversely, the grotesques, the carved figures that do not carry water, were purely decorative or symbolic, but both types of carving underscored a core medieval belief that even the mundane necessities of drainage were worthy of divine or demonic attention. The silent, watching monsters were in fact the world's most dramatic rain spouts. Chapter 20, the architecture of terror, the striking of the centering. The single most dangerous and decisive moment in the cathedral's construction came after the last stone was laid and the mortar had set. This was the moment of the striking of the centering. Centering was the immense, custom-built wooden scaffolding, often a temporary cathedral in itself, that supported the entire vault or arch during construction. It was essential, yet terrifyingly expensive, and occupied valuable space. Once the keystone was tapped into place, permanently locking the arch into a state of compression, the wood structure below became structurally obsolete. The centering had to be removed, or struck. This process was slow and performed with extreme caution. The wooden supports were gradually lowered, often by slowly unscrewing massive wedges at the base. The entire workforce, the master mason, and the city itself would hold its breath during this moment. It was the ultimate stress test. If the master mason's geometry was flawed, If the buttresses were not perfectly aligned, or if the foundation had subtly settled, the entire structure, the vault, the walls, and decades of effort, could collapse into a spectacular, fatal pile of stone and splintered timber. The moment the centering was gone, and the massive stone roof held itself up, locked only by physics and geometry, was the true triumph of the Gothic builder. It was the moment the hypothesis of flight became the reality of permanence. Chapter 21. The unseen costs, the human liability. The sheer length of the construction cycle, which often spanned over 180 years, meant that the vast majority of workers labored anonymously and died before the structure reached completion. The highly paid master mason himself, though possessing a substantial annual salary and a specific contract, was bound to the site, knowing he was merely a link in a chain of architectural succession. Even the highly personal banker mark, inscribed onto each finished stone for piecework payment, eventually disappeared into the unseen joints and high walls. The system that ensured a mason was paid by volume also ensured his signature was soon absorbed by the structure itself. The human cost was also literal. The constant threat of falling stone, collapsing scaffolding, or the inevitable exhaustion from operating the human-powered treadwheel crane meant accidents were a regular, grim part of the ledger. The cathedral became a continuous project, absorbing the lives, the faith, and the physical labor of entire generations. It stands today not only as a testament to engineering prowess, but as a record of collective humility. Thousands of skilled hands, forever anonymous, dedicated their fleeting lives to a monument designed for the infinite line of history. The great stone sentinel watches over the city, forever silent, eternally anchored. Chapter 22. The alchemical mortar, fire and water. The immense blocks of stone, perfectly cut and dressed, were not merely stacked on top of one another. They were bound together by a material whose creation was an intense, chemical process. Lime mortar. This process began far from the construction site. With fire, limestone, the primary building material, had to be quarried and then subjected to intense heat in a kiln. This process, known as calcining, transformed the raw calcium carbonate into quicklime. Quicklime, a highly volatile and reactive substance, was then treated with water, a process called slaking. This violent chemical reaction created the putty-like binder needed for the mortar, which was finally mixed with sand to create the binding agent. This specialized material was essential. It was not just filler. It was the flexible, self-healing glue that allowed the cathedral to settle and shift over centuries, keeping the immense stone mass tightly connected. The medieval builders were therefore not only masons and engineers. They were chemists, mastering the precise mixture of earth, water, and fire necessary to achieve eternal rigidity. Chapter 23. The geometry of the modulus. While the master mason used his compasses to calculate every arch and vault, the entire cathedral plan was often controlled by a hidden, singular mathematical reference point. The modulus. The modulus was a basic unit of measure, sometimes the width of the central aisle, or the span of an arch. This single measurement dictated the proportional ratios of every other dimension in the structure. The designers relied heavily on practical, constructive geometry, not complex theorems. They utilized simple ratios derived from the square, such as the square root of 2, to govern the layout of the entire floor plan. This meant that the width of the nave might bear a strict proportional relationship, based on the square root of 2, to the height of the walls or the thickness of the external piers. The cathedral became a self-referential machine, a massive, three-dimensional geometry problem, where every part related perfectly to the whole, all derived from a simple, starting measurement. This rule of thumb, manipulation of compass and ruler, ensured a vital continuity, that even if a master mason died, his successor could decipher the underlying geometric code and continue the construction seamlessly, following the invisible, mathematical harmony. Chapter 24. The Environmental Shadow. The spiritual glory of the rising stone structure casts a massive environmental shadow across the medieval landscape. The demand for stone was staggering. More stone was quarried in France alone during the High Middle Ages than in the whole history of ancient Egypt. But the demand for wood was equally destructive. Vast quantities of primeval timber were consumed, not just for the permanent roof trusses, but for the constant need for scaffolding, for the centering that supported the arches, and for the timber framework of the huge treadwheel cranes. Furthermore, the continuous need for lime mortar meant that the cathedral project placed relentless pressure on local woodland for charcoal, needed to fuel the kilns that burned the limestone. The construction of the Cathedral of the Infinite Arch was an all-consuming, industrial project, dependent on the systematic consumption of the surrounding forests, linking the sacred stone structure directly to the systematic clearance of the medieval wilderness. Chapter 25. The Sound of the Century. If you could stand on the construction site of the Cathedral of the Infinite Arch in the year 1285, you would be overwhelmed not by silence, but by noise. The rhythmic thud, thud, thud of the mallet against the chisel was pervasive, the constant sound of piecework payment being earned, one strike at a time. There was the creak and groan of the massive treadwheel crane, powered by men walking inside the wooden cage. The ratch, ratch, ratch of the rope being wound as a 1-ton block was slowly lifted hundreds of feet. Below that, the heavy clop of oxen and carts dragging the raw materials, and the low, constant hiss of the slaking lime pits. The medieval cathedral was not a place of quiet contemplation during its construction. It was a continuous industrial symphony of rhythm, effort, and relentless noise, a continuous soundscape of human ambition, a noise that lasted for nearly 200 years, only to be replaced by the quiet, compressed silence of the finished stone. The finished building stands today, silent and permanent, the final, quiet monument to the deafening labor that brought it into existence. The work continues, slow and rhythmic, in the darkness. Chapter 26. The Spire and the Spectacular Lie. For centuries after the initial construction concluded, the Cathedral of the Infinite Arch stood largely as the original masons had left it, a heavy monument to stone and silence. But in the 19th century, a grand wave of architectural restoration swept across Europe. The spirit of the medieval builders was reawakened, often by architects who sought not to replicate the past, but to perfect it. This movement gave rise to the most dramatic structural feature of the entire cathedral, the towering final spire. Yet this pinnacle, soaring 96 meters into the Parisian sky, was a spectacular lie. The original medieval spire, often smaller and less ambitious, had long vanished. The new spire was entirely the imaginative creation of a 19th-century architect named Violet Leduc. commissioned purely for ornamental function. This architect chose to reinvent the building to fit his own Gothic ideal, resulting in a structure that was visually medieval, but constructed with 19th-century ambition. Chapter 27. The Weight of the Modern Ghost. This ornamental spire added a terrifying, concentrated load onto the centuries-old structure below. It was composed of approximately 500 tons of wood, a massive, combustible structural cage. This wood was then entirely encased in 250 tons of lead sheeting for waterproofing and aesthetic finish, adding immense, unrelenting dead weight high above the stone vaults. The flying buttresses, designed centuries earlier to contain the lateral thrust of the original roof, now had to support the weight and wind loads of this massive, ornamental ghost. The final, visible glory of the cathedral was a highly complex structural hazard, waiting for a tragedy that would only occur many decades later. Chapter 28. The Continuous Construction. A cathedral is never truly completed, only temporarily abandoned. The structure remained a work in progress for at least 182 years, and then became a site of continuous modification for hundreds more. Even today, architectural clues remain, showing that the permanent stone was built to accommodate temporary access. Look closely at the walls, and you can still see the regular rows of small holes, the putlag holes. These were the apertures into which the temporary wooden beams of the scaffolding were inserted. When the scaffolding was removed, the holes were often filled, but sometimes they were simply left open. These quiet, recurring gaps in the masonry are permanent records of temporary necessity, transforming the cathedral into a document of its own construction process, an endless cycle of rise and modification. Chapter 29. The Statues That Walked. During the 19th century restoration, the copper statues of the 12 apostles and the 4 evangelists were placed around the spire's base. As the decades passed, the copper oxidized, giving the religious figures a haunting, green-gray hue. A final, remarkable twist of fate occurred centuries after the last master mason had died. Restoration work was planned for the copper spire and statues, just days before the structure's ultimate destruction. The statues were painstakingly removed and lowered to the ground for restoration. They were saved by chance, by the meticulous, rhythmic schedule of modern preservation work, escaping the fire that would claim the structure they were meant to guard. The metal figures of the apostles, the silent watchers of the stone structure, literally walked away from the flames. A strange, bizarre footnote in the structure's long, dramatic life. Chapter 30. The Eternal Ledger of Geometry. The story of the Cathedral of the Infinite Arch concludes with the quiet rhythm of persistence. It stands today, a testament not to a single genius, but to the unbreakable geometric principles established on the long-forgotten tracing floor. The structure is held up by stone, by the hidden grip of iron reinforcement, and by the precise proportional ratios that still govern its soaring height. The anonymous stonecutter, the mason who earned his wage by the banker mark, the laborer who traded his sweat for spiritual forgiveness, all contributed to a monument whose existence defied the limits of the human lifespan. They built not for themselves, but for an infinite line of history, a sacred construction meant to last until the world itself was remade. The great stone sentinel stands, absorbing the light, forever permanent, eternally compressed, the ultimate, quiet record of anonymous human effort. The work is complete, slow, and rhythmic. In the darkness, Chapter 11. The Invisible Anchor. Foundations in Earth and Prayer. Before the first massive block of dressed limestone could rise into the air, a far more tedious and critical task had to be completed. Deep in the mud and damp earth, the immense weight of the future stone mountain demanded an equally monumental base. Foundations for these great structures often required digging trenches far deeper than contemporary domestic buildings, sometimes reaching 12 feet or more, until solid, load-bearing ground was reached. This was the work of the lowest-skilled laborers, digging and excavating the dark earth, a work often paid for not just in coin, but in spiritual currency. The crisis of stability. The medieval builders did not have modern engineering analysis. And crucially, they were not masters of Roman concrete. They had to rely on stacked stone and rubble to create a stable base. Once the trench reached stable earth, the space was often filled with thick layers of compacted rubble and mortar. This foundation served as the invisible anchor, a massive hidden stone slab, designed to evenly distribute the colossal weight of the entire structure across the potentially unreliable ground beneath. Any error in this initial, hidden phase, any undetected weakness or pocket of soft clay, meant that the entire, century-long project was doomed to eventual, dramatic failure. The subsequent structure, reaching hundreds of feet into the sky, was utterly dependent on the stability of this dark, unseen geometry laid down by anonymous hands. Chapter 12. Geometry's Secret: The Tracing Floor. The master mason, the true genius of the project, was not just a manager of men and materials. He was the keeper of a sacred, constructive geometry. His designs were not theoretical blueprints on expensive parchment, at least, not initially. They were calculated and drawn in full scale, directly onto a specially prepared surface on the site. This surface was the tracing floor. It was a large, flat area often made of plaster or smooth stone, set aside within the construction lodge. Here, the master mason would take his primary tools and inscribe the cathedral's complex forms. The master's tools. The master mason's instruments were simple, yet capable of infinite complexity. Let us visualize the instruments. First, the skirret, an implement working from a central pin to draw the perfect curved lines for the foundation layout. Second, the pencil, for delineating the building in draft form, instructing his workmen. And most importantly, the compasses, which enabled him to determine the precise limits and divine proportions of every arch, every window, and every vault segment. The mason's geometry was not the abstract mathematics of Euclid, but a practical, constructive approach. They used simple, repeating ratios derived from the square, such as the square root of 2, to govern the proportions of the entire floor plan. This geometry was often passed down secretly, a professional necessity to maintain their elite status, and it was applied directly to the stone. Templates, full-sized patterns for complex elements like window tracery and vaulting ribs, were first worked out on this tracing floor, then transferred to wood or metal molds. These molds were then taken directly to the quarry for prefabrication, ensuring every block met the master's geometric ideal. This process meant that the entire, vast cathedral, from the smallest rib stone to the highest flying buttress, was geometrically standardized, a medieval system of prefabrication enforced by the rule and compass. The geometry was the project's spiritual DNA, a secret code that defined every single stone's place in the monumental design. Chapter 13. The Fire and the Fall: A Century of Risk. The long construction timeline, sometimes 2 centuries, was a constant struggle against time, gravity, and sudden catastrophe. Gothic architecture was an audacious, high-stakes gamble. Builders were continuously experimenting, pushing the limits of stone physics, without modern structural theory. This experimentation inevitably led to horrifying structural failures. The ultimate test of the master mason's design was not completion, but survival, catastrophe, and correction. In several great cathedral projects, the pressure from the newly completed stone vaults proved too much for the initially thin walls, and major sections of the nave collapsed, sometimes years or decades after they were first raised. A sudden, catastrophic collapse meant the destruction of decades of labor, massive financial loss, and often the death of workers. These structural failures were not just tragedies. They were involuntary, high-cost engineering lessons. In response to a collapse, the master masons did not abandon the project. They improvised and reinforced. This is precisely why many surviving cathedrals, including the imagined Cathedral of the Infinite Arch, feature multiple layers of structural buttressing, visible evidence of original design flaws that had to be corrected rapidly and massively after a partial failure. The threat from above, even successful completion, offered no respite. For the greatest threat to a stone church was not gravity, but fire. Above the heavy stone vault sat the immense wooden roof structure, a rigid cage of ancient timber designed to distribute wind loads. This roof, covered typically in heavy lead sheeting, was an ever-present fire hazard. The stone vault below was specifically designed as a fire barrier, a massive, non-combustible shield, intended to contain the burning timber roof and prevent the fire from reaching the interior liturgical space below. This fear of fire, more than aesthetics alone, justified the expense and effort of lifting all that heavy stone hundreds of feet into the air to create a ceiling of eternal compression. It was an architecture born from ambition, but disciplined by the constant, chilling risk of catastrophe. Chapter 14. The Light of God, the Glass Complex. The structural miracle of the flying buttress and the stone vault had one ultimate purpose: light. By diverting the outward thrust externally, the massive, load-bearing walls of earlier Romanesque churches were dissolved and replaced by vast, soaring expanses of glass. The light flooding the interior was meant to be the visual manifestation of the divine presence. The artisan's alchemy, the creation of the stained glass, was an industrial complex unto itself, requiring highly specialized artisans, the glaziers. Glass was incredibly expensive and difficult to manufacture, requiring precise control over temperatures and the mixing of exotic minerals to create the intense, saturated colors: cobalt for blue, copper for green, and lead or manganese for deep purples. The glazier's workshop was often set up close to the main site, where the full-scale templates from the tracing floor were adapted. Hundreds of thousands of small, hand-cut pieces of colored glass were required for a single window bay. Each piece was painstakingly fitted into a structural framework of narrow lead strips, or cames, which both held the mosaic together and added the thick black lines that defined the images. When the sun finally struck these towering walls of glass, the interior was transformed into a realm of rich, shifting color, where natural daylight was filtered and colored by scenes of biblical history, transforming the stone structure into a floating spectacle of light and theology. The heavy, earthbound logistics of the quarry and the crane ultimately served this single, ephemeral goal: to capture the sun and turn it into colored, divine narrative. The work continues, slow and rhythmic. In the darkness,